Okay, so in the remainder of the semester, what we're going to do is I'm going to give you a brief survey of what other problems are available. Actually, we will also talk about the ones that we've already talked about. This survey is initially prepared for the ISOLDE conference last year, and unfortunately it covers essentially everything that exists in the literature until 2005, but after that I did not have much time to update it. However, I think the last 3 years is maybe I'll update it next year, so we'll just suffice with what we have here. Okay, I'll go through these very quickly. Historically, the first paper in network location is Hakimi's paper, which you've already covered in the class. And prior to this, there was a paper that appeared in Chinese mathematics back in 1962, which actually gave a Goldman-type tree-trimming procedure for the one medium problem. That was your exam question, if you remember, if you placed it correctly. So actually, I think we should also mention that, Hua Lo Keng and others. There are many others, actually, so I can't remember all these Chinese names. But that paper is a predecessor. Hakimi is the core paper, so we cite it for that reason, and that's the beginning of the network location history. The stuff that appeared in between 1964 and 82 is already reviewed in the paper Tansel, Francis, and Lava that appeared in 83 in Management Science. You've taken a look at these two-part surveys for your research. So since then, since 1964, it's been 44 years, and during these years, the number of papers that have been published in this area is in excess of 500. Actually, if you go through a Google search, of course, you'll obtain 5,000 or probably more. But when you actually filter them out and directly look at the ones that deal with either mathematical programming procedures or analytical procedures, it boils down to approximately somewhere between 500 and 600. Okay? There have been a number of books published. Handler and Merchandani is the first book, published back in '79. Unfortunately, it doesn't cover all the stuff that I wanted to cover in the class. And there's an edited book by Merchandani and Francis that appeared in '90. Daskin wrote a book in '95, but none of these books are really as comprehensive as I would normally expect them to be. Nevertheless, they are good reference books if you need to look at them. There's only one survey directly on network facility location. That's the one that appeared in Management Science in '83. There are other related surveys, so if you're interested in them, I can provide you with a list of these papers. Okay? What is network location? It involves locating one or more facilities on a network to serve demands that arise at nodes or sometimes along arcs. And problem types can be actually differentiated depending on the type of facilities you have. You may have point facilities, which is the stuff we've looked at. Sometimes you may have structures, subnetworks, as treated as facilities. Okay? And you may be locating only on top of nodes, which is what many people do, or you permit locations of facilities along arcs, which is a bit more complicated because your search space now contains infinitely many points. Demands can be discrete demands. In other words, you would have a finite number of demands that are the nodes normally, or sometimes you may have continuous demands along arcs. defined by a probability density function of some sort. You have a question?
And
yeah.
locating sometimes may be done into embedded space of the network for monitoring reasons, not on the arcs, not on the nodes, but on the space.
I see. Okay, this we don't have it, but sometimes NS is actually looking at a problem of that sort. Whatever space you embed your network, suppose you embed it, say, in the two-dimensional plane, sometimes you may be locating facilities outside of the network, on the plane, for example, to serve, say, detect things that may be going on the network itself. So that's a third possibility, yes. Objectives can be push or pull type. You've seen only pull types of objectives so far. And the environment may involve competition with other facilities or no competition. The problems you've seen so far are no competing or facility location problems under no competition. Okay? The state of the nature could be certain or random or uncertain, and we've looked at only deterministic problems that involves known states of nature. So, pull types, objectives, the most well-known ones are the p-median, p-center, and the related cover problem. You've already seen these things. There is the so-called p-median with communication problem and p-center with mutual communication problem. These are somewhat similar to the p-median and p-center problems, except that in the p-median and p-center problems, you don't have any interaction or service relation between facilities themselves. They only serve demand points. Whereas in problems with mutual communication, facilities that you locate may also give service or receive service from other facilities. So there's an interaction between facilities themselves. The push type of objectives are relevant when you want to locate, for example, hazardous materials or dump sites or things of that, or nuclear power plants and so forth. In that case, of course, you want your facilities to be away from the points that you serve. And in that case, that gives rise to maxisum or maximin or anti-cover type of problems. If we have time this week, I'll go into these as well. I plan to, at least. Other types of problems involve multiple objectives. That's a possibility. You may actually be locating structural facilities, which means you are taking subnetworks or subtrees as possible facilities. Robust location. Anybody knows what robust stands for in this context? Robustness stands for the following in any decision-making environment. If you have point estimates for your input parameters for the problem, then when you solve the problem optimally, then relative to those input parameters, you have an optimal positioning of yourself. Okay? However, if you don't have point estimates for your parameters, for example, in linear programming, suppose your costs are not point valued, but you have, say, only intervals for estimates of cost parameters. In that case, your inputs can be actually any one of many possible inputs. If you think of your inputs as a vector, there are many possible vectors. You don't know which one will be realized. There's no probability or possibility distribution associated with these. So still, you've got some estimate where these input vectors are coming from. So how do you, in that case, decide optimally, whatever optimal means, you have to define that first, relative to unknown parameters. But they are not completely unknown. At least you know from which set they come from. Okay? So robust location is something of that nature, and competitive location is the type of problem you would have when you try to locate a facility, then the competitor is also in the market. So depending on where you want to locate, he positions himself accordingly. So you have to also play the game accordingly. You have to think of what he would do when you position yourself in a particular way, so you would actually try to outmaneuver the competitor. That's an interesting situation. All right, so let's begin with the first pull type of objective, the p-median problem. You locate p-identical facilities to minimize the total cost. You've already seen this model. You're trying to minimize an objective function, f of x, where x stands for p points selected from the network. And you have f defined by weighted sum of distances, wj times dx vj. And each capital D function is defined by the distance of the ith vertex to a closest element of the point set x. And the first result we've seen on this is the node optimality result of Hakimi. Remember that we had this housetop or concave two-piece linear function for the distance from any fixed point to a variable point along an edge. And that concave function leads to concave sum of functions, which is concave, which means the optimum restricted to an edge will occur either at one endpoint or the other endpoint. That's the node optimality. And so it simply states that there exists always an optimal solution on the nodes of the network. Hakimi actually proved this for the one median case in his 64 paper, and then he actually also proved it for the p-median case, the general p, in his 65 paper. So this leads to order of n squared algorithm for the single median problem. And for the general p problem, it leads to a finite but exponential algorithm, and p plus 1 times p algorithm. Okay? In those algorithms, of course, you simply enumerate all possible choices of p nodes from the network. So certain extensions of the node optimality result have been also given. Hakimi gave it for the one median case. Hakimi's 65 paper generalized it to the p-median problem. I also gave you proofs for that. Goldman and Mayers in 65 generalized this to concave costs. In other words, if you replace each weighted distance in the summation by a concave cost function of the distance, then you have still node optimality. That was one of your exam questions also. Okay? All right, Levy extended the result to concave costs as well as capacitated facilities. So normally we don't have any capacity restrictions. Goldman then gave a little bit more general case with concave costs again with distinguishable facilities. In the p-median uncapacitated problem, you don't distinguish between facilities because you just take the closest one. Whereas if you have capacities or other distinguishing features, that's the generalization in Goldman's paper. Hakimi Maheshwari gave a generalization for concave costs, capacitated facilities, with multiple commodities being served from the facilities to the demand points. Wendell and Herter, concave, capacitated, multiple commodities with multiple processing stages. Merchandani O'Donnell, they gave a one median generalization when arc lengths of the network are random rather than deterministic. And Merchandani O'Donnell also give supporting medians and conditional p-median problems and show that node optimality still holds under these conditions. Sometimes node optimality fails. One problem where the node optimality fails is proved by Frank. These 66, 67 papers of Frank are not well known. They are very important papers. So if you happen to do research in this area, you should be aware of them. But many people are not aware of those papers. I know that, okay? Now, the first paper, maximum probability absolute R-median problem. In this problem, you've got probabilities associated with realizations of weights, node weights, okay? So in the 66 paper, each vertex weight has a distribution of itself. In other words, there are no correlations between different vertex weights. In the second paper, 67, they are jointly distributed. So that's the only distinction. But let's just look at the first one. In the first one, now when things are realizable probabilistically, of course you can go for the expected median by simply taking the expected value of each weight and solving a deterministic problem. That would be an expected median. But is that the best you can do? The other alternative is you can actually give a bound on the objective value. You want your objective value to be less than or equal to R, for example. And you would look for a point or median on the network where if you place yourself or your facility at that point, you are guaranteed that the probability of serving the nodes within that upper bound is maximum. So you're trying to maximize the probability of serving the nodes, given that your objective value will be less than or equal to some upper bound. It's similar to robust approaches, actually, except that you know the probabilities in this case. So in this case, node optimality fails. Also, in the second case, when they are jointly distributed, again, it fails. There's another generalization, well, not generalization, but another p-median, one-median problem using MG1 queues at vertices, and that's by Berman, Larson, and Chu. Again, the p-median, the node optimality property fails in that problem as well. The exact solutions for the p-median problem, we've talked about these. Well, this problem is, first of all, NP-hard, even if the network is a planar graph of maximum degree 3. This is due to Kariv and Hakimi, 79. And the well-known integer linear programming formulation is what you see on the screen. Xij is 1 if, well, let's put it this way. Xjj is 1 if there's a facility at node j, okay? And Xij will be 1 if your node I receives service from node j. And these conditions, the first constraint simply tells you that you should choose, you should assign every node I to some facility, okay? And the second constraint, I will receive a service from node j only if there is a facility at j. And the last one simply says that you would choose only p such facilities. And Cij is the cost of serving node I from a facility located at j. So that's an adaptation from the fixed charge location problem of earlier model, Balinsky model 61. Okay. So based on that, this is the history of what has happened in the solution methodology for this problem. Essentially, all of them are based on the IP formulation I gave you. Revel and Swain, they actually solved the problem using the integer linear programming formulation I gave you. They solved the linear programming relaxation with branching bound. The second one, Jarvin and Rajala, Sinervo, they again used branching bound. Garfinkel, Nebe, Rao, they used the linear programming relaxation coupled with group theory and dynamic recursion. Narula, Ogbi, Samuelson, they use Lagrangian relaxation. Kornejos, Fisher, Nemhauser, that's a famous paper. They give several results on incapacitated facility location problem, and those results have been later used for solving p-medium problems. Mavrides generalized the p-medium problem and solved it using Lagrangian relaxation coupled with the methodology available for incapacitated facility location problems. Galvao, AD paper, that's again quite well known. He used the dual of the linear programming relaxation and used branching bound. Buffy and Karkazis, they solved a problem with 206 nodes where the number of facilities is 45. That's a large problem actually for total enumeration. And they used incapacitated facility location problems with variable fixed costs and adjust the arcs, adjust the costs according to P. And essentially what they do is they take the summation of xij's equal P constraint, they multiply it with a Lagrange multiplier, a weight, and throw it into the objective function, and they search on lambda, the multiplier value. Okay, that's why fixed charges become variable actually from iteration to iteration. Christofides and Beasley, they again used the Lagrangian relaxation and subgradient optimization, and they solved the problem up to n equals 200. Beasley improved this to n equals 900. That's the largest solved to the present time with p equals 90. And Merchandani, I've never learned how to pronounce Ojit. I guess it's Ojit. And Wong, they used nested dual approach with Lagrangian relaxation coupled with Erlen-Cotter's dual ascent and dual simplex method, and they solved the problem up to n equals 200. Now, Hooker's paper in the bottom is important. It gives several important theoretical results on the p-medium problem based on convex costs. So the weighted functions, weighted distances are convex costs. He shows that node optimality fails. And he identifies actually the so-called tree-like segments. And I talked about this to one of your classmates actually, to you. If you think of a vertex and an edge, when you have a variable point on the edge moving from one endpoint to the other, and you have a fixed vertex, the distance from the fixed vertex to the variable point is a two-piece linear function. You remember that, okay? Now, this two-piece linear function can be linear or can be two-piece linear. If it's two-piece linear, there's a peak point. That peak point is actually where the distance becomes the largest. That's called an antipodal of that particular vertex under consideration on this edge. Now, on a given edge, every vertex could possibly induce an antipodal point, a peak point. So you may have up to n such antipodals, order of n, okay, antipodals. Now, suppose for each edge you actually computed the locations of the antipodals, you marked them. If you think of each antipodal as an artificially defined vertex, then you can expand the vertex set by simply adding these points to the vertex set. And of course, the edge set also becomes different because now you've got adjacent antipodals which give you new edges, smaller edges, sub-edges of the original edges. So when you think of this, this is important stuff. If you take any two adjacent antipodals on a given edge, when you look at the distance function from a given vertex along that segment, there will not be any peaks anymore. Everything will be linear. That's absolutely very important, in case you haven't noticed it by now. A lot of people don't actually think of these things. Nevertheless, I know that that's a very important theorem, well, or observation, let's put it that way. So, for any such segment defined by two adjacent antipodals, all these vertex-related distance functions are linear. They are either increasing or decreasing. So, if you isolate such a segment and take it as a, say, simple linear segment or simple edge, you can assign to one side all those vertices that visit that endpoint and then start increasing, and to the other endpoint all those vertices whose lowest points are at that vertex, that point, with increasing value along the segment. That would give you a tree-like segment. And if you solve the problem with whatever facility you're trying to locate restricted to that segment, everything is like a tree then. Okay? So you can use the tree network methodology using that observation, except that there are a lot of such segments. How many? Well, on a given edge, you've got order n adjacent, order n antipodals, so that would give ON segments per edge, so you would multiply that with the number of edges. Okay? All right, so Hooker gives several such results, and his p-median algorithm actually boils down to choosing p such segments from all possible segments, which can work only for small problems, but he did not generalize it. All right, and Rees published a bibliography on p-median in 2004. How many people looked at that bibliography during your search? You looked at it. Did you find it useful?
I don't remember, but I know the name.
You know the name, okay. Well, it's a bibliography, so it should help. Okay. There are several heuristics, but I'm not going to go through them. And I guess the heuristic concentration in more contemporary years seems to be the dominant one. Unfortunately, Ravel has passed away, and Rosing, he was also somewhat ill. I'm not sure if he's alive or not. Nevertheless, there will be other people who will be pursuing heuristic concentration, I believe. Conditional p-medians. Some of you actually probably ran into this during your literature search. What do you do in conditional p-medians? Actually, this is, I asked you a conditional problem for the center version, okay? It's really not difficult. You already have some Q facilities placed on the network. And then the total number of facilities on the network will be P. So you want to place P minus Q new facilities. You want to still minimize the total cost, the sum of weighted distances. And a demand point will receive service again from a closest facility, but the closest one could be one of the old ones or it could be one of the new ones. Depends on how the new ones are situated. It turns out that node optimality still holds for this problem. And Minieka actually solved the case when the new one is only 1. Okay, P minus Q is equal to 1. And he simply redefined the entries of the distance matrix in a certain way, and the problem is solved like a single one-medium problem. Berman, Simchi, and Simchi-Levy, they solved the conditional problem by solving unconditional P+1 medium problems, where the P plus first median or facility is a single facility that represents the combined effect of all existing medians. Okay? Dresner provided a heuristic for this problem. And how did you handle your P-center problem, the conditional one? You should have handled it the way I told you on the board on that day. Okay, whatever. For the special case of tree networks, P equals 1, P equals 2, or P-median case, we've got a number of results. Goldman and Witzgall, they gave a localization theorem which localized the one median at a subtree. All of this work is for tree networks, okay? Goldman then gave the tree trimming algorithm that I asked you on the exam. So the problem is solvable in ON. Now, what is important about the tree trimming algorithm? Without having to know the edge lengths. So it works for every edge length as long as you have the same tree structure. So it actually solves an infinite family of problems defined by the same structure, whatever the edge lengths might be. Okay, that's important. Karive and Hakimi actually showed that the centroid of a tree is the same as the one median. Merchandani, Ojit, they gave a two median algorithm in n squared. Matula and Kolde gave a p median algorithm which is n to power 3 and p squared. Shu then gave a p median algorithm that works in n cubed p time. Karif Hakimi gave a more efficient one that works in n squared p squared. I was planned to cover the Karif Hakimi algorithm, but it would take, well, it's only a pure algorithm. It has no analytical component to it. It's more data processing than anything else. It's a dynamic programming type of procedure, so you do things efficiently. If you're familiar with dynamic programming, then you would understand the material better. But it takes a long time to explain the stuff to newcomers, okay? That's why I sort of chose not to do it. Tamir gave a more efficient version of this algorithm, and he made it more transparent, which works in n squared p time. If the network is not a tree, but rather just a path, then even more efficient algorithms can be developed. One is by Hasin and Tamir. It works in NP time. The p-median with continuous edge demands. In the remaining few minutes, let me just tell you what the problem here is. The red statement at the top tells you what this problem involves. Demands in the old problem, discrete version, are point demands. Okay, they arise at vertices. In this case, if you have a street with many occupants along the street, then each household is a demand point. So you have a continuum of demands. Just think of it that way. When you have a continuum of demands along edges, you may also permit mass demands somewhere at some points along the edges. For example, a high rise or something. Okay. So under such conditions, how do you deal with the p-median problem? Minieka is the first one to look at this. He used point-to-edge distances and showed that the node optimality fails under such circumstances. and solved the problem for p equals 1 using point-to-edge distances. Hansen and Labe, they showed a finite dominating set consisting of vertices plus edge midpoints is available, so that leads to an n-squared algorithm. And solved the tree case with general P in linear time. Also, they solved the general conditional median problem. And you can see the other ones. This problem, we haven't really looked at it that much, so I'll just let you read the other ones, and I'm going to close the lecture with that, okay? Because you seem to be a little bit, I guess, tired maybe when so much information is coming so fast. Huh? Okay. Let's just finish it here.